Today's Jones seminar speaker is Dieter Stoeckel. He's been involved in the development and commercialization of advanced materials for over 40 years. He became interested in the shape memory effect during the late 70s while researching alternatives to thermostatic bimetals. Ever since, he directed material research, process development, and product innovation with shape memory and superelastic alloys, specifically Nitinol. Dr. Stoeckel received a MS and PhD in physical metallurgy from the University of Stuttgart, the Max Planck Institute for Metals Research in Germany in 1969 and 1972 respectively. The title of his talk is Shape Memory and Superelasticity from Scientific Curiosity to Life-Saving Technology. Please welcome Jesus.
It doesn't blink green. It does. Good afternoon. It's a pleasure to be here on this beautiful Good Friday. I was a little surprised that you would have an event like this on a Good Friday. In Germany, I don't think I would have pulled anybody into a seminar room on Good Friday. So I applaud your interest in this topic, and I certainly, I'm very excited about talking about this. This is a technology that has brought a lot of frustration, but also a lot of deep satisfaction during the last 30 years or so. And I hope that I can kind of share some of this excitement about this with you. I called this talk From Scientific Curiosity to Life-Saving Technology because, shape memory technology was ridiculed for a long time as something that only hardcore Martensitie transformation scientists would be interested in. But over the years, we did create a market, and if I may say so, during this talk, this is probably my career's worth of involvement in the Nitinol technology, at least for 30 years. Before I did Nitinol, I was involved in metal matrix composites, which is another just fantastic field to work on. But this one is something that makes you addictive to, and maybe during the talk I'm going to throw in a few little stories about how these things work. So let's start with this guy. I don't know who in the auditorium remembers Uri Geller. He was one of these people that could actually deform metal by just concentrating his thoughts on. Now, this I don't think is Uri Geller. I think this is an impersonator, but anyway, this guy can bend a spoon. So the question is this magic, or is his willpower, or what actually is it? Now, if you take a closer look at what he uses, it's no magic, no willpower. He takes a piece of metal, he deforms it. It would stay deformed if you let go, but if you heat it up, it would return to its straight shape. And as metallurgists, we want to know why that is, and we look into the material and we find that this is a twin Martensite up there to start with. When he deforms this rod, he detwins the twins, and when he heats it up, that the material transforms back into austenite, which at this temperature is the stable phase in this particular system. So we can clearly state that he used the shape memory effect of whatever alloy, most likely nitinol, might have been something else. And here we have the full cycle of that. We start with a cubic structure. It's actually a cesium chloride structure, superlattice, ordered structure. And above these transformation temperatures, typically I'm only talking about the transformation temperature, although it's actually 4 different transformation temperatures, and it's a band of temperatures. But from a functional perspective, only one is important, and that is this uppermost. So if you cool this particular structure down to below this transformation temperature, it transforms into a monoclinic structure, and this is characterized by twins. The metallurgists in this room know what twins are. They are a special arrangement of atoms. And if you notice, the transformation from here to there does not change the location of the atoms. So this is a diffusion-less transformation. At temperatures down here, this one is the stable phase. And if you now deform this twin martensite, you can de-twin by basically moving all the zigs into zag direction. So that goes one after the other, and at the end, you have a fully de-twinned structure, which is now deformed, and it stays deformed, until you heat it back up over this transformation temperature, and because the atoms still have not changed their location, it finds back to its original shape. So this is what we call shape memory or thermal shape memory. There's another effect in this whole thing, and that is when you take this austenitic structure above AF and you deform it, it does not deform through conventional dislocation movement and stuff, but it goes directly into de-twinned martensite. That's what we call stress-induced martensite. Stress-induced and deformed martensite. So in this one, this whole thing is above AF. So if you are above AF, above this transformation temperature, you can deform the austenite into deformed martensite, but when you let go, it springs back and it just reacts extremely elastically. So you can see that in this no, this is not particularly straight, I just realized. But this is your screen that makes it look warped. Anyway, we have the austenite. This whole test is done at a temperature above AF, and you can deform it, but when you let go, it jumps back into the straight configuration. Stress-induced martensite, and we call that superelasticity because the amount of elastic recovery that you can get is much higher than in stainless or any other metallic material for that purpose. It's about 10 times higher than steel elasticity, and that's why we call it superelasticity. It's a little bit of a marketing term because I think the scientists have called it pseudo-elasticity. But when you sell something and you say this is pseudo-elastic, then you as an engineer would say, I'm not going to buy anything that's pseudo only. So that's why we called it superelasticity, and it goes much better, I can tell you. Anyway, so the whole thing is a thermoelastic martensitic transformation. That is something that has been well known. Actually, in the mid 1930s, a Chinese researcher found this effect in gold cadmium, if I'm not mistaken. And then in the mid 50s, Hornbogen in Germany did his thesis on those transformations in copper-based alloys. But it was not until 1963 that the effect in nickel titanium materials or nickel titanium alloys was found. And it was actually discovered at the Naval Ordnance Laboratory here in the United States, and that's why the material is also called Nitinol, N-I-T-I, and N-O-L for Naval Ordnance Laboratory. So they discovered this material when they tried to come up with a material for, I guess it was for submarines. It had to be high strength, corrosion resistant, and it had to be non-magnetic. And they formed these, I mean, those are the anecdotes. They said they rolled the sheets and stuff like that, and then they formed the hull of the ship, and then when they started welding, these formed sheets would all go back to their rolled and straight condition, and they wondered what it was, and and did some further experiments, and found this Martensitie transformation in nickel titanium. And from now on, I will call this material Nitinol. Nitinol is by far the most important shape memory alloy in the market today. It's actually the only one that made it to commercial applications. The copper-based alloys, we tried that in the early 70s. They are not corrosion resistant, particularly stress corrosion. Cracking happens a lot. They are not stable, and for medical applications, they wouldn't be used anyway because, I mean, they are not biocompatible. So Nitinol has an ideal combination of properties. It's a real engineering material, high strength. You can deform it. You can deform it because otherwise we couldn't make a product out of it. But it's not as easy as other materials because it tends to want to go back to its original shape. So, and that happens during production also. If you look at the binary system, nickel and titanium, for us right now, only this very small compositional range is important. We see that there is a transformation in the temperature range between 100 and minus 100, and if you look at the concentration, it's mostly between around the 50%, and that is atomic percent composition. And this is essential because I described earlier, you have to have an ordered structure, and we have to have as many nickel atoms as we have titanium atoms to make this thing work. So this is extremely important that you meet the composition, and you can see we actually can work from an engineering perspective. We can work with a range of compositions, basically from 49% nickel to something in the neighborhood of 51% nickel. This is a little too white. We stop at actually 50.8. So. And as you can see, in this range, you get transformation temperatures basically between 100 and minus 100 degrees, which tells you that when you melt this material and you are not dead on what you're looking for, you're off with your transformation temperature. So 0.1 degree, 0.1% change in composition produces a temperature difference of 10 degrees from your targeted transformation temperature. So if you take an alloy from this composition, say a little titanium rich, you get shape memory because now you have a transformation temperature that is above room temperature, and if you do a tensile test with this alloy, you get a tensile curve that looks like this one. You have a first elastic range here, and then you get something that we call a plateau, a stress plateau, where you get a significant amount of strain without increasing stress. And then at this point, you get a second conventionally elastic range and then plastic deformation. Now when you unload, the unloading follows this curve, and it does not get back to the starting point. Now, if you take an alloy from the other side of this range, and this is the 50.8 atomic percent alloy, the transformation temperature is below room temperature, and if you do a tensile test there, you get the same kind of curve on loading, but when you unload, you can see that the unloading curve comes back too, and that we have a pronounced hysteresis of the stress-strain curve here. And this is very important because the most successful applications of nickel titanium, particularly in the medical world, make use of this particular stress-strain curve. So if we compare that with stainless, everybody knows stainless has a linear elastic range here, and then plastic deformation, everything from here to there is plastically deformed. If you would unload from here, you would have permanent deformation, or from here you have permanent deformation. On the other hand, nitinol has this hysteresis, and even after whatever 10% strain, you still get back to the starting point. Now, this is an alloy where we do the tensile test above the transformation temperature of the alloy. If we lower the temperature, let me just do this real quick. If we lower the temperature, then we just basically move the entire curve down, and it goes below the x-axis, so that's not usable, but it's exactly the same mechanism, the exact same atomistic process. This piece that we now have that looks like it's permanently deformed, this can be thermally recovered. So if you heat the sample up back to where we were, then you would move this curve up, and the deformation is recovered. I already explained, we don't have to go into the details of this thing. This strange stress-strain curve, which is not common in other materials, this is caused by this deformation mechanism by detwinning, and I tried to kind of show how that works. You have the zigzag arrangement, and then you de-zig or you de-zag this thing until you only have zigs or zags, and then you have this deformed shape. If you look, on the other hand, for the deformation of steel, the really plastic deformation, you have dislocation movement, and when the dislocation has moved through your lattice here, then you have a permanent deformation there that does not go back. Okay, what can we do in nitinol? We can bend rods, but nobody is interested in bending rods. That's not true. I can show applications where bending rods is actually the product. But we can solve problems that don't exist. That was what we were told early on. I mean, when we try to, and this is a teaching, if you want. If you try to sell technology, that's always very difficult. You want to sell a product. If you want to sell technology, that's what's called technology push. It will never work as well as market pull. So you have to have an application, you have to have a need for something, and then you say, okay, I can solve this problem using this. But you can't go in and say, I have this. Can you give me a problem that I can solve that with? So this was, we had the wrong start, but if you are persistent enough, you're going to find people that do have a problem that wants to be solved. And you can publish. Unfortunately, I don't have the absolute numbers, but I just wanted to show this thing. If you do a search for references that reference nitinol, shape memory, or superelasticity, you see that starting around 1970, shape memory goes up like amazingly, superelasticity nobody really talks about. Although this is the real thing, as you will see. This is where you can make a product and where you can make money with. This other stuff, this shape memory, has never made it to commercial success. Okay, here are some of the learnings from my career early on. We obviously did military research and stuff like that, so we came up with these pipe couplings. A clever idea, fantastic, but economically not feasible. Yeah, what you would do is you would machine the sleeve out of Nitinol with an inner diameter that would be smaller than the diameter, the outer diameter of the pipes to be joined. And then you cool this down in liquid nitrogen, you expand it, you slide it over the ends of the pipes, and you heat it up, and it shrinks onto the ends and joins the ends of the pipes. Now this, as I said, technically fantastic, and it provides a very tight seal, and you can actually do that even while fuel is in these pipes. If you would want to do that by welding, you would blow up the airplane. So the idea was to repair leaks with a system like that, because this is always cold. It has to be in liquid nitrogen. And the funny thing was, the technicians, this was, by the way, all done at Raychem, who was a huge pioneer in this technology. So we would have technicians that would travel to the sites where repairs had to be done, and they had a dewar with them with liquid nitrogen in them and an expanded coupling, and they would go onto an airplane with the dewar, and the white fog would come out of the dewar, and nobody would complain. Today, I guess they would shoot you at the airport when you would show up with something like that. Anyway, obviously the logistics were completely impossible. You can't ship or travel with product that's at minus 200 degrees or whatever liquid nitrogen is. So it did not work economically. But Raychem managed to get some real press about these things, because they did a repair of a gas pipeline on the bottom of the North Sea. So this obviously is a project that's a multi-million-dollar project, and it does not really matter what the sleeve costs. I mean, the sleeve was probably $100,000 or something like that. But it got a lot of press time. Raychem lost a ton of money on it. And the same with other applications. This is a repair in I think it was in a painting plant or something like that, with paint fumes going through. So that's where you do things like that. But again, I show that from an engineering perspective, absolutely great. But from an economics perspective, impossible. But those were the good old days. I mean, the companies actually did spend money on trying new things. Today, it's much more difficult. This one is something that I would say is reasonably successful. What we did is we replaced the steel spring in an oil regulator in the automatic transmission of a Mercedes with a shape memory spring, and that automatically made this valve temperature dependent. So when it's cold, it would switch different from when it was warm. So they could adjust the cold start behavior of the transmission. So I traveled the world because we thought we had it cornered now. We had the automotive industry. So I visited every automotive company and said, we have this great thing that helps you make your shifting smoother. And none of them had a problem, not a single one. It was only Mercedes, because Mercedes was the only company that had a hydraulic transmission. Everybody else was already doing electronic transmissions, and there you don't need it. So again, there was a economic failure, as were all these other things. You know, louvers of headlamps. You know, there was a disk drive thing. That was a resettable fuse, and this was the stupidest of all. There was a Barbie that had mechanisms in it that would make the arms go up and down, and you know, with a battery, and you would push this thing. You would heat these wires in there with a battery that was in the stand, and the battery would drain in 5 minutes or less. But this was at Toys R Us. Toys R Us sold this stupid thing. I mean, I think they made somewhere up in the neighborhood of 100,000. But it just shows, you know, the kids play with it 5 minutes, it's kaput, they throw it away. Nobody took it back. So obviously the company went out of business anyway. But those are the things that just don't work. There's a rule in Nitinol all-shape memory, and that is, if you can solve a problem with something else, do it. Don't use Nitinol. If you find other ways of doing it, and there are tons of ways to make a dull move. Here we go. This is a good one, though. This is a good one. This is, you have to imagine, this is early 80s or something like that. Pipelines in Saudi Arabia. Pipelines are coated with a polymer on the ID because the oil is corrosive. So when they weld these pipes together, they destroy the polymeric coating. So what Raychem did was they created this cage that would expand under the weld zone and press some polymeric coating epoxy stuff to the ID of the pipe. Great thought, was fantastic. It did work actually. They built little gizmos to get this cage in. But then the oil companies decided they could mix some corrosion preventive stuff into the oil, and the pipes would not corrode. So again, 100 million in the sand, literally. But still, I mean, it was a fantastic project. Now let's get to superelasticity, because I get excited about these things and it takes too long. This is when we really got the commercial success, and that was with consumer products. You probably remember the cell phones that you could pull an antenna out. Oh, the young folks don't remember those, but basically every cell phone had an antenna, and then you pulled it out, and you had better reception or whatever it was. And this was always Nitinol. That was a real big market. That was hundreds of tons of material. That was really good, but now the iPhone has no antenna, I guess. So there's no need for Nitinol. Fishing lures, that still goes strong. Amazingly, undergarment wires apparently is a good market too. Unfortunately, we were never in that market. So sporting goods in general, faceplates for golf, for putters are not allowed by whoever that is, the PGA or somebody. So that wasn't particularly successful. But this one was successful too. And this is actually superelastic eyeglass frames. By the way, what this little guy said, don't do that with your glasses. This was a commercial that ran in Germany. Eschenbach was a company that actually pioneered these superelastic glasses. And today, you probably don't even know that you have superelastic glasses. But I would still recommend don't try it, because if it isn't, then you're out of luck. And we don't have liability insurance for those kind of things. Why is this black now? No, anyway, but that just said a consumer product finally kind of brought the breakthrough and opened the market. So let's get to the medical side of things. If you look at, we did a little search for patent applications with nitinol in the title, broken down into certain areas, but all out of the medical field. And if you look at this, it starts, say, around the early 80s, and it kind of peaked 2005, 2007. So this is when all the major development took place. We started our company, by the way, in '91, right at the beginning of this boom in medical devices. And why is that so interesting? Early applications of nitinol for medical applications were orthopedic in nature, like these bone plates that would contract to fractured bones and put pressure on the fracture site. This is actually from it's hard to read. I think this says 74, so this is very early. This one are bone staples, same concept. You implant them with these legs open, and then you heat it up, and they close and pull the fracture together, the crack together. And the way they heated those was with current. They would pass current through it. And you see that it looks like a cattle prod or something like that. So you would heat that thing up by passing current through it, and it would close. And that was in use. It was not a big success, but it was in commercial production. Now this is the first real product that started a whole new range of applications for nitinol in medical instruments. This one is a simple hook made out of nitinol that can be pulled into this needle and then pushed out in the body. And this is what they call a needle wire localizer. This is to localize a breast tumor. So the patient is in the X-ray unit, and they find a tumor in the breast, and they put this needle next to the tumor. They push the wire out, and it kind of locates the tumor, and then the patient goes to the surgeon. The surgeon follows the wire and can find this tumor and operate on it with a much smaller incision than if they would have to kind of look where that thing is. And this concept has then been used for lots of other products, instruments. This is an old one. It's a variable curvature spatula or variable curvature needle. Here are ablation needles. This is an irrigation electrode for electrophysiology. And basically all the applications today circle around that. You deform a superelastic component into a small delivery system, and you deploy it in the body. This is the concept. And it doesn't have to be a simple wire like this needle wire localizer. It can be real complex devices, like this thing is an implant that closes a left atrial appendage in the heart, or this is a Vena Cava filter, and we're going to get to these things. This one is actually the biggest thing. It's called EndoCatch. It's organ retrieval bag for laparoscopic surgery. So if your gallbladder is removed, they have to take that deceased bladder out of the body without kind of exposing it to the surrounding organs and tissues. So this is a pretty big thing. I don't know if I show that, but it all goes through this tiny little introducer, or whatever you want to call this thing. And then it goes through a small incision or through a trocar in your body, and the surgeon works with that. So very small incisions are possible. We're going to talk about a few different applications, although I would like to focus on vascular implants. And the reason for that is that this is by far the biggest market for this material. The end user market for these products is somewhere in the neighborhood of $2 billion. $2 billion, and you can say the component market then is about 10% of that, so 200 million is what the manufacturer of the implant itself can see. But still, this is big. I mean, this is considerable. Okay, so we're going to talk about stents, and stents is the great breakthrough in this technology. Then filters is also older applications. Heart valve frames is the newest application, and probably with a huge potential also if it works. And then occlusion devices to repair structural heart defects. Sometimes I have to click twice, and I don't know why. Remember this thing? See, this is, what did I say, early 80s or so, late 70s, when Raychem repaired pipelines. They built a stent. That's what they actually did. It's a huge one. I mean, it had something like a meter diameter or something like that. But it is the same concept. It's a cut pattern that can be compressed to a small diameter, and then when heated, it would expand and open. I mean, here it doesn't have to open anything, but it has to coat the ID surface of this pipe. And the funny thing is about this, we had a poster for this product in a conference room at Raychem, and one day a customer of ours from the medical industry came by. That was probably late 80s or so. He saw this picture, and he said, "This is exactly what I need. But I want it that small, and it has to do this and that, and but it is this thing." And that's what we got exposed to this particular technology for the first time. We didn't know what a stent was back then. I mean, we were all metallurgists and material scientists and things like that. We didn't know these things. We had played with military stuff. We built bombs and no, not bombs, but the whatever you call these trigger mechanisms and stuff like that, all from shape memory. But here we go. Somebody came and actually wanted it for a really cool application. So self-expanding stents, where do we actually use those? And how are they used? I mean, we produce the stent in the open condition. It's then compressed into a delivery system and into a catheter, basically. The catheter goes through the femoral artery, either wherever you have to go. In this case, it went into the brain, into the carotid artery, and there you pull back the retaining outer sheath, and then the stent opens up and lines the vessel. When we created this little animation, that's a long time ago, we omitted the plaque actually in this vessel. You know, you would ask, why the hell would you put a stent in such a beautiful vessel? You wouldn't. You know, we forgot to put the plaque here in this animation. So typically these vessels are almost closed with debris and stuff like that, and that's what you actually want to open. So typically what they do, particularly in the heart, they go in with a balloon, the balloon is open, they basically press the plaque into the vessel wall, take the balloon out, and then you have blood flow again, and that's angioplasty. Everybody knows what that is. The problem with that is that there's a high occurrence of restenosis, so that's when they say, okay, then we put a stent in that's going to help keep this vessel open. And in the heart, in the coronary arteries, they do not use the self-expanding stents because it's so small, and the cardiologists are used to actually pump up a stent with a balloon. So the coronary stent is a steel stent or a cobalt chrome material that can be plastically deformed. It's crimped onto a balloon. They go into the coronary arteries. They blow up the balloon and deform the stent. And then you have a rigid piece sitting there. Now these stents, these self-expanding stents, go into the periphery. So your peripheral arteries, you know, like the femoral artery, the carotid, everything outside the heart, this is where self-expansion comes in. And the advantage, at least in some applications, particularly in the carotid, is that a peripheral vessel can be deformed through outside force. Yeah, so if you wear a tie and you tie it too tight and you have a stainless steel stent in the carotid, you may run the risk of deforming that, and that does not come back. A superelastic, a self-expanding stent would come back. It's more physiologically compatible, if you want. Okay, here are a few of these stents. Stents are made from wire, they are made from sheet, they are made from tubing. Most of them are made from tubing, laser cut tubing. But simpler versions like this coil stent is just basically a coil. I don't know if this is in use much. This one is a knitted construct from Nitinol wire. This one are wires that are welded together. It's very rigid. That never made it to much success. This one is a braided construct. Problem with braided ones is they typically they call it foreshortened. Why they call it foreshortened, I don't know. When you compress this thing, it gets longer. So in the delivery system, it's longer than when it's deployed. And if you want to really accurately position that, you got to know how long your stent is when it comes out. So these stents, they do not shorten much. So that's why most of the stents in the market today are made from tubing, from laser cut tubing. Some of them have radio opaque marker. We might as well mention that at this point, that Nitinol is not particularly radio opaque. So in order to see the stent in the body under fluoroscopy, you have to have, for example, a tantalum paddle welded to the end of the stent, or this is a tantalum rivet in an eyelet. This one is a nickel titanium platinum alloy. This particular company says it's better compatible with a Nitinol, but it's all the same. This one is actually gold, which is not good because of galvanic corrosion. So if you have a gold marker on a stent, you would have to coat this afterwards so that there is no galvanic corrosion effect going. Okay, so why do we actually use Nitinol for stents? We also already said elastic deployment is a huge advantage, but there are others like kink resistance, and I think there should be a little video showing what that is. You can basically take a Nitinol stent fully expanded, and you can completely crush it, compress it multiple times, and it will always come back to its original size, which is important because, as I said, some of the superficial vessels can be deformed from the outside. Here's the most important aspect, which comes from this hysteresis in the stress-strain curve. We call that biased or path-dependent stiffness, meaning that this product is less stiff on unloading than it is on loading. What does that mean? If you look at this part of the stress-strain curve, when you superimpose these numbers here, stent diameter in this direction and hoop force, we can simulate the loading and unloading of a stent. So you have your fully expanded stent, say it's a 10 millimeter stent or something like that. You compress it into a 2 millimeter delivery system. So you compress the 10 millimeter stent into a 2 millimeter lumen of the catheter. You would follow this curve, the loading curve. Yeah, here's, say, 2 millimeters. You go into the body to the delivery site, you unload, you let the stent come out of the delivery system, and now it follows the unloading curve to the point where it hits the vessel wall. And the important thing is with self-expanding stents is that the stent should always be a little bigger than the vessel itself. So for example, a 10 millimeter stent you would put into an 8 millimeter vessel. So when you unload the 10 millimeter stent, you have basically 6 millimeters to go until you hit the vessel. You have 2 millimeters to go until you hit the vessel if it's 8 millimeter, and then it sits there. And at that point, it exerts this very low force. It tries to get bigger and exerts a certain force to the vessel. And we call this force chronic outward force, and that's very low. And but when you then try to compress this stent, say through outside forces or external forces or through a spasm or whatever, when the vessel wants to contract, the stent would oppose this force with this stiffness. So it's much stronger when it's actually being deformed. So that's what we call biased stiffness or path-dependent stiffness. Here's another important aspect. Because this unloading curve is so flat, you have a lot of tolerance here in terms of how much you oversize. It doesn't really matter if your stent is 2 millimeters bigger than the vessel or 3 millimeters bigger. The force it exerts is not much higher. This is just to show how we test these things. I don't think this is that important. I'd rather go to a few other things. An important aspect of this whole use of nitinol for implants is it's what we call biomechanical compatibility. If you compare, and this is just the qualitative appearance of the stress-strain curve, not any quantitative data, but if you compare the shape of that curve with any natural material in the body, it's very similar. See, hair has a hysteresis, bone has a hysteresis, tendon has a hysteresis, so nitinol is somehow similar to the natural materials in the body. And we just do believe that this helps. I mean, nobody can prove it, but it's a good argument. At least I think it is a good argument. The whole development of the applications went or coincides with the development of the material itself. For example, before 95, we did not have tubing, so you couldn't make a stent out of tubing. You would have to do braided wire or something like that. So, but we developed tube drawing around 1995, and now tubes are available from several vendors. And we also developed the laser cutting of this stuff. And now with the tubes, you can laser cut, and you can make the most complicated shapes. After laser cutting, what you do is you push a tapered mandrel through this thing and do a heat treatment, and that locks the bigger shape in place. And depending on the final size of the product, you have to do that multiple times, so you can't go from the as cut to the finished size because that would put too much strain on the material. So you do that in 2 or 3 steps, and do a heat treatment, 500 degrees or something like that. That locks the shape in, and it also creates the right transformation temperature. So we have ways to kind of adjust that up and down a little bit through heat treatments. And then obviously the surface treatment is very important. The stent is first blasted with little glass beads or whatever it is, and then electropolished, and the final product has a fabulous surface. Oops, why is that I put that in just before we started. That's why I was not prepared for that. We had a discussion this afternoon about AAA devices. AAAs are abdominal aortic aneurysms that are typically deadly when they burst. They have to be surgically operated on, which is a big mess. And people are trying to do that endovascularly now with percutaneous delivery of a prosthesis. This happens to be one that has been in the market for a while, the Gore excluder. It's a Teflon graft with nitinol stents woven in or sewn in or whatever you would call that. It's a major operation, but very successful and obviously by far not as invasive as open surgery of a AAA. This represents a huge market potential because these prostheses are very expensive. They're about $10,000 a piece, but the overall cost advantage compared with open surgery is tremendous. I think that shows the concept. Another product that is very successful is the Vena Cava filter. The inferior vena cava is the big vein that carries the oxygenated blood back into the heart. And the problem is when you are in the hospital, for example, for a long time after a trauma or something like that, blood clots can form in your legs and they are transported up into the heart and eventually into the lung, and then you would have a pulmonary embolism. So what they do is prophylactically they put filters in this vena cava, and they are basically all nitinol these days. Some are made out of wire. This one is the Simon nitinol filter. That's the oldest one that was actually developed in the 70s. Believe it or not, amazing, and it's still around. This one is an interesting one because it can shoot little suture wires out of these legs and actually anchor the filter in the vessel wall. This one is a very successful symmetrical one. You can put that in from jugular or from femoral very easily, and this is a new option filter. A little video to show what that does. And I think I have to speed up a little bit. I mean, this is animation. In real life, it's not as easy as it looks here, but it comes close. So these blood clots are huge that can form in your legs, and they are caught in this filter, and then after a while, the blood that flows around them is actually going to dissolve them. And at that point, you want to take the filter out. Most of the old filters are permanent; they stay in, and it doesn't really hurt you, but it just doesn't feel right to have a metal implant somewhere where you don't need it. So that's why people these days look for retrievable filters. And all the new ones that come into the market are retrievable, and they are basically all made from nitinol. Here's another hot topic, heart valve frames. People try to repair deceased heart valves percutaneously these days too. Normally, this is open heart surgery. You get a new valve implanted and things like that. Very invasive, long recovery periods and stuff like that. So they are trying to do this percutaneously also. I have one here that's the Vena valve, and actually I think that thing has a So this is the newest product in the market. Actually, they get very high valuations. CoreValve was one of the first of them. A nitinol frame, and I think a bovine valve, and the company went for $700 or $900 million to Medtronic. You know, after the first clinicals and things like that. And another one is Sadra, also a nitinol valve in the early stages, $300 million to Boston Scientific. So this is big money. And obviously it does help the patient. I mean, when I say there's money to be made, it kind of sounds, I don't know, profane or whatever you want to call that. But you know, it really helps the patients. Here's a bunch of other defects that can be repaired. You know, we have in the heart, you can find atrial septal defects or ventricular septal defects, and they are basically holes in the heart that have to be plugged. And there are typical products are this double helix or whatever you would call that. This one is a wire braided thing. That's very, very simple, but very useful. And yeah, there are other occlusion devices that we probably don't have to go through because they are basically the same as the other ones, just a different type of usage. Here's an appendage that has to be closed, all nitinol. And I threw this one in because we had a discussion this afternoon about porous nitinol. You can make nitinol porous through a process, a very interesting process that's called combustion synthesis. So what you do is you take nickel powder and titanium powder, you put it into a quartz tube, you compact it, and then you put a little ignition thing in one end. Basically a current that you pass through that heats it up to a critical temperature, and then it's an exothermic reaction. And this thing doesn't necessarily explode, but there's a wave going through this material that makes it fuse the particles, and then you get something like this spongy material that has a very good properties like bone ingrowth and those kind of things. So this stuff is being tried for spine implants and other traumatic kind of stuff. So there's a ton of other things that could be said. Let me just close with with one statement, and that is, again, don't use nitinol if there are other solutions, because I mean many people have lost a lot of money by just trying to do it with nitinol just because or whatever, you know. Don't do that. And other than that, I can just say it's unbelievably satisfying to work on products like this that really help the customer, the patients, and we do talk to patients, and they are very, very grateful and thankful. Thank you very much. It is a problem in certain areas. And it's not necessarily a clinical problem. It's a perceived problem, and there are certain groups of physicians, like from the orthopedics industry, that are concerned about nickel allergy. We have not had a single case with any implant. I mean, in the cardiovascular, there has never been a problem. We have tried to get over this hurdle of nickel allergy, but you know, as a manufacturer, you can't go out and say there's no problem because they're just not going to believe you. That has to come from the physician. They have to do the studies or whatever it is, and they don't exist. But it's the orthopedic industry that has a problem. Everybody else doesn't. And it's a perceived problem. I don't think there are any proven cases of nickel allergy in those implants. Yeah.
The stents and other applications have a sheath. How do you put the sheath on and what the sheath is?
You mean like in this AAA?
Yeah.
That was PTFE. That's PTFE. The gore prosthesis is PTFE.
And it's somehow sewn on?
It's sewn on. It's a very complicated process. This one, the gore is kind of, how would you say that, woven into the structure of the stent. Because the stents are just sinusoidal rings. Other laser cut stents have to be actually sewn on individually. And I think one prosthesis has like 800 little stitches where they actually stitch that to the stent frame.
And this is all done when it's open.
Yeah.
Doesn't get affected when it's closed.
I mean, this is obviously a concern, and this has to be done in a way that the polymeric material has to pleat somehow, or whatever you call that, so that it can be compressed. You will never get it down to the size that you would get the Nitinol stent to. That's why these AAA delivery systems are typically much bigger than regular stent delivery systems. But they are still considered percutaneous. I think if they are smaller than 18 French or something like that, which is somewhere in the neighborhood of 10 millimeter or so.
One more quick one on your porous Nitinol that you showed us in that last slide. Is the push for that an orthopedic application, or is that simply to make it different deformable structure?
It is. That's a good question. I think it's like many of these other things. The technology was there first, and then they realized that this material had a modulus that's very similar to bone. And they tried to kind of put that as an artificial disc, or for fusion, obviously, not for functional discs, but for fusion disc, and found that the bone ingrowth is very good. It was not made because somebody said, I need something that would do well in the spine. And we don't have any other application for that stuff so far. I mean, for us, it's, again, a technology that fits perfectly into the other stuff, and if somebody comes and says, you know, make a product out of it, we will.
Thank you, everybody. And if you have any
Thank you.
questions,
No, I'm available, so.